Hello and welcome to some skills work. Again, you learn skills by doing, so let's have a go. Or maybe you've had a go and you can mark it as you go. Um, so we've got enzyme catalyzed. Oops. Um, yeah. So I've got hydrogen peroxide, and really kind of it's irrelevant anyway. But it's yeah. So I've got data for three bits of tissue with different catalase activity. You can see that they vary massively in terms of if I was doing a bar chart to show 3000 you wouldn't see the two, so we've gone for a log scale graph here. You can see on the y-axis. So yeah, so we need to plot this graph. So I'm going to do it a bit faster. I'm going to call that A, B and C. So yeah, so this is going to be A, B and C, and I've got a ruler on my iPad, so but I'll do my best. So yeah, so liver's 3000. So yeah, so remember the log scale, that this is 1000, 2000, 3000. So it's this line here. So let's get that one in. So that's A. Again, I would use a ruler. I don't need to shade it in, but I'll just give it a little shade so you can see it a bit easier. B is 500. So yeah, 100, 200, 300, 400, 500. So that's here. Oops. That's B. So that should be straight across there. So that's B. And C, which most people got wrong in year 12, it's two. So the bottom line is 1, so it's this line here is 2. So that's 2. And what people forget is that I need to label the axis. The y-axis is already labelled, so this just needs to be tissue here. Again, people miss that out because they think they've labelled the axis because they put A, B and C here, as in liver, brain and leaf, and they think that's labelling it. No, but that is just labelling the bars. It's the same as putting numbers on an axis. So yeah, so there was one mark for knowing that this is a bar chart graph. There's one mark for plotting the bars correctly, so understanding a log scale. There was a mark for making sure that the bars were the same width, and they were separated by the same size gap. And there was a mark for labelling the axis as well. So yeah, did you get 4 out of 4 on that one? If you did, very few year 12 did. Then we've got a little unit conversion. Again, cube units are notoriously difficult. This is where I'd probably say, right, well, 1 centimetre cubed equals, well, that's 1 centimetre by 1 centimetre times 1 centimetre. I mean, I wouldn't write this. So that's the same as 10 millimetres times 10 millimetres times 10 millimetres, which is 1,000 millimetres cubed. If I times 10 millimetres by 10 millimetres by 10 millimetres, so 0.034 centimetres cubed, I need to multiply that by 1,000, so that comes in at 34 millimetres cubed. Again, very few people get that right as well because they think that there's 10 millimeters cubed in a centimeter cubed, and they confuse, like a linear measurement with area and volume. And then so our calibration curve was constructed using known concentrations of betalain. That's the pigment in beetroot, as it says here, which then had their light absorbance measured using a colorimeter. Complete the table to show how 20 centimeters cubed. Again, I always like highlight the numbers or circle the numbers. I've got a highlight here, so I can highlight it. 20 centimeters cubed is what I need to make up using, I've got my stock solution is 5 molar or 5 moles per decimeter cubed. I've got some distilled water as well. And there's numerous ways of doing these questions. I just think it's easier to get like one done and then use that to do the rest, if that makes sense. And if I look here, this one's 2.5 molar. Well, that's half of 5 molar. So that's quite an easy one. That if I want 20 centimeters cubed of it, 10 centimeters cubed needs to be made up of my 5 molar solution, and I need to dilute it by half. So therefore, yeah, these two numbers add up to 20. So I'm fulfilling my 20 centimeters cubed. And yeah, 2.5 is half the strength. So yeah, I'd have to have, it does be half water, half solution. So that's quite easy, I think. Crucially, a lot of people didn't get that. They got the first one, did the first one, and then got stuck, which sounds a bit crazy, but yeah. So don't always start on the first row. Look to see where the easy bit is. Often, they want a 3 mark question to be like a discriminator. They don't want people who can do these to get 3 and everyone else get 0. They want it to be like some people get 1 mark, some get 2 marks, and a few get 3 marks, and some get 0 marks. That's a well-designed question. So let's do the next bit in this table. So I can slot in 16 here as well. That's quite easy because I know that my volume has to add up to 20. And and then I'm right. Well, I've got four centimeters cubed out of the 20 is stock solution. So yeah, so 4 out of 20 is it's 0.2 into it. Yeah, because 2 out of 10 is 0.2. 4 divided by 20. I shouldn't really have to check this, but it is a weekend. Yeah. So it's 0.2. So 4 divided by 20 is 0.2. So 0.2 of 5 molar has to be the concentration. So here I put, so this is just 1.0. So what I've done there is, if we take the 2.5 one, 10 divided by 20 is a half. Half of the 5 molar must be my concentration here. So I've done that. 10 divided by the final volume, 20, gives me the fraction of the 5 molar that I need. So I can use this one to get this one. So 4 divided by 20. 4 divided by 20 is 0.2. Therefore, 0.2 times 5 gives me 1. Okay. And then once I've got 1, I would just think, well, 0.2 is a fifth of it. So 4 divided by 5, I just need a fifth of that one. So this just becomes 0.8. And therefore, this is, 19.2 because it adds up to 20. So I got my 0.8 by knowing that 0.2 is a fifth of 1. Therefore, it must be a fifth of 4 as well. So it just works in proportions. Again, you can only really learn how to do these by doing them, and you can just make up a volume, make up a concentration, make a little table like this, pop some numbers in, leave some blanks, and have a go. And in terms of marking it, bring it to a workshop or something, and we can see if you got it right. But it's dead easy to get these have to add up to 20. Then we've got a little uncertainty question. So a cube of beetroot was cut with side lengths of 5 plus or minus 0.5 millimeters. Calculate the volume of the cube of beetroot in millimeters cubed. That's good. So it's millimeters and millimeters cubed. So that's no drama. And quote the absolute uncertainty. So there's an easy mark and a hard mark. So let's get the volume first. 5 cubed equals 125 millimeters cubed. So I've got my 125 done, and then I need to get my uncertainty sorted. But I've got 1 mark for doing 5 cubed, as it were. So then we have to do the uncertainty. The first thing we do is work out the percentage uncertainty. Equals, so it's 0.5 divided by 5 multiplied by 100. As in, what percentage is the uncertainty of the actual value? So so 0.5 divided by 5. It's 10%. That's nice and easy then. Sorry, 0.5 divided by 5 1 times 100. Yeah, it is 10%. You're cringing here, aren't you? I can't do simple maths, but I'm just making sure that I don't make an error. So I've got 10% uncertainty on the length. Now, the rule is with combining uncertainties that if you are multiplying up, you add the uncertainties. So I need to do 10%, then I need to, for every kind of times 5, I need to add on another 10%. And so because I've cubed it, I need to do 10% times 3. So my total uncertainty, percentage uncertainty, is 30%. Because I've cubed the 5, I therefore need to add together 3 lots of 10% uncertainty. Therefore, 125 multiplied by 30% is my absolute uncertainty. So 30 divided by 100 multiplied, so 0.3 times 125, yes, it's 37.5 millimeters cubed. So yeah, so that's my answer, 37.5. Hard, but yeah, it's just knowing the rule that you have to go for this percentage uncertainty first, and then you work out the absolute uncertainty, and you don't multiply the uncertainty, you add them together. Why? Because that's the rule, I think. And then a calibration graph showing the absorbance of light against Betteling concentration was produce a straight line. So this is basically describing this graph. So I've got, it says light absorbance, so light abs, and here I've got time, sorry, not time, I've got Betteling concentration, Betteling conc, and that's in percentage. Well, no, it's not, it's in moles per centimetre cubed, so that's in molar, and that's, this one's percentage, isn't it? And I've got the quality equation y equals 18.6x. So it's going to be a line that starts at 0, 0, and it's y equals 18.6x. And if I had the graph, I could get my 68% light absorbance, go along to the line, and come down and find the Betteling concentration. However, as soon as it follows that, I can just sub the numbers into this equation, give my answer to 2 sig fig. So I've got a light absorption of 68. So the hard bit is knowing that 68% is the y value. So 68 equals 18.6x. So x equals 68 divided by 18.6. So 68 divided by 18.6 is 3.6559, etc. But I want 2 sig fig, so yeah, so it's 3.7. Crucially, if I get my y and the x the wrong way around, I'll end up with, I would have done 18.6 multiplied by 68. 18.6 times 68. I'd be saying, oh yeah, it's 1,264.8 molar. It's obviously wrong. Yeah, it could have been, and I'd have to give it 2 sig figs, so 1,300 molar. Well, this question was using 5 molar stock solution, and this number 3.7 makes sense because if the maximum concentration is 5 molar in this question, then yeah, down to 3.7 molar is makes a lot of sense. And then on to D, a piece of beetroot was placed in 20 centimeters cubed, water for 1 minute. All right, it's just describing the experiment here. But yeah, the crucial bit is that it fell from 3.6 molar to 0.3 molar. So yeah, just do the difference. So it's 3.3 divided by the original 3.6 because it's a decrease times 100. The most common maths question in A-level biology is a percentage increase or decrease. And times by 100 equals 91.7. Give you to the nearest whole percent. So yeah, it's 92. And that again makes sense. If it's gone from a number, 3.6 to almost 0. Well, if it was 0, it'd be 100%. So I'm pretty confident I'm right there because it looks right with those numbers. So yeah, sense checking my answer. And the good old question: how do you describe how a boiling tube containing the beetroot from question 2D will be maintained at 70 degrees C for 1 minute? It's quite a warm temperature, 70 degrees C. So yeah, so this is where we need to be really clear about how you would actually do it. Don't just say, use a thermometer and add hot water when you need to, yeah, you're going to get 0 for it. So you need, there's 1 mark for your thermometer in the boiling tube, with the beetroot, yeah, and is checked. Yeah, I'm checking the thermometer in the boiling tube, and then I'm going to place boiling tube in a beaker of water at 70 degrees C. It's going to cool. Yeah. Therefore, I need to add boiling water, or heat with the Bunsen burner. Yeah. Add boiling water. Yeah. When temp drops. Below 70 degrees C. So yeah, so it's saying that you can use a thermometer where it is and check it, put it in a beaker at 70 degrees C, and add boiling water when temperature drops below 70 degrees C. Okay, it's only for 1 minute, so it's not going to be too onerous, is it? But yeah, that was a skills test, folks. So yeah, did you find something that you would have got wrong? Again, the average mark was, is it 17? I think it is. Yeah, the average was about 8 or 9, I think it was. And the average mark's like a high C pushing a B, a bit like on a mock. So yeah, but there's 4 marks for for just drawing a bar chart. And they have asked, bar charts in the past in the A-level exam, so it's not something that never appears. Anyway, that's it.